Now, another very often used mechanism that is seen in organic reactions inside enzymes is redox reactions. And we have a few electron carriers that is available to use to do redox. NAD plus and NADH is the two forms of a electron acceptor and an electron donator in our mechanisms, and so I'll show you how it works. Now, most of the time, what we write is NAD plus, okay? But what I'm doing is I'm going to show you the functional organic structure of the ADP plus, that is the electron acceptor. And so what you can see is ADP is part of it, ribose is there, and then this organic structure is the portion that is going to be part of the organic reaction. Now, this organic structure has to accept an electron pair, okay, in the form of a hydride. And you can see at this position, there is one hydrogen, and after the reaction, there are two. And so this is the place in which the hydride is going to be accepted. Now, the base is going to deprotonate one of the two potential hydrogens. Now, there's one hydrogen because here it is. There's a hydrogen attached to this oxygen, but in the product, that's gone. But there's a secondary hydrogen that's on this carbon that is also missing. And so what we're going to do is we're going to have the base deprotonate the hydrogen. This is the most acidic hydrogen, the easiest one for a base to abstract. The electron pair is going to form the double bond. That means there's too many bonds to carbon. Now, in organic chemistry, if a hydride is a leaving group, this would be automatically wrong. Very few cases do we have a hydride leave, but in an organic reaction inside an enzyme, if I have a hydride acceptor, that's an acceptable organic reaction. So this hydride will attack the ring. Okay, when that attacks, then I have too many bonds to carbon. I'm going to move the double bond and force it over, but now I have a consequence. I have too many bonds to carbon at this position, and then I will take the electrons and place them onto the nitrogen. What happens is now the nitrogen as the product is neutral, and so I go from an N plus to a neutral, and I've also added a hydrogen, so I go from NAD plus to NAD, no positive charge, and an H. And so I have, in essence, oxidized the hydroxide to the ketone here and have produced NADH. Now, you notice that this is an equilibrium, so there's a reverse. And so in reverse, this can also donate a hydride. And so the electron pair can re-aromatize the ring, and this hydride can actually attack. Negative charge will attack at the carbonyl, which is partially positive, and what's going to happen is this will pick up a proton and become the hydroxide. Now, most often what I'm going to write is an organic reaction where I'll write NAD. I'll write NAD here with a hydride attached, and so my mechanism I could write and make it look like this attack at the carbonyl and that pick up without having to write the entire organic molecule of the NADH. Also, I can consequently take this hydride, and when I'm going to accept it, I can attack at the NAD plus, but I am articulating exactly where inside the NAD plus it's accepting and in where it's coming from in the NADH. Now, one other electron carrier that we use very, very often is FAD and FADH2. It is similar in that it's going to accept hydrides. And so if I take a look at this, I show the organic structure of the FAD, And over here, I have FADH2. And so now I'm going to pick up a proton. I'm actually going to pick up 2 protons. And so the reaction is what you're going to oxidize, the electron acceptor, and a proton is going to be important in this reaction. I will form a double bond as the end product. And so I will then allow the base to abstract. Now at this point in time, I can abstract either of the 2 potential hydrogens that will need to be removed. Depending upon the influence of the R group, you may have an advantage of one over the other, but at this point we don't, so I can take either. And so what I will do is I will abstract one, the electron pair that is left over forms the double bond, and now I have a leaving group which is a hydride, and I'll show that. And I then attack the nitrogen. Now, the nitrogen on the top of the ring is sterically less hindered, so most likely that's where the attack's going to be, although you could end up attacking at this, depending upon the orientation inside the enzyme. The electron pair will have to move because I have too many bonds, and then this pair of electrons here has to move onto the nitrogen. And it'll be negative for just a short period of time, which then attacks. But instead of showing that, what I'm going to do is I'm going to show that that pair of electrons goes onto the nitrogen and then picks up the hydrogen. And that is the secondary hydrogen that is here, the most likely candidate for the hydride that was derived from the original organic molecule is at the top. In reverse, again, we can have, let me go back. In reverse, what we can have is a base abstract that proton, form the double bond. This forms the double bond that was originally, and now I have a hydride that leaves, attacks at either side at this moment in time. Usually it's the orientation of where the FADH2 is in relationship to how it's bonded. Again, the R groups that are around might influence stability, and then this picks up the proton to go back to the original molecule. Okay, the last redox reaction that we would like to go to is a reduction. Whereas the previous have been oxidations, now we're going to reduce. And so what we're going to do is use the substrate NADPH. This is NAD structure, but at the bottom of the ring structure there's an additional phosphate, which then allows it to bind in different active sites and is normally used for reducing power. And so what we're going to do in terms of the mechanism, the lone pair of electrons on the nitrogen will reform the aromatic ring, cause that to reform, and now a hydride will be a leaving group that can attack at the carbonyl, and then the electrons will kick up and pick up the proton to create a reduced intermediate. Now, most of the time, I won't write out the NADPH. What I will articulate is NADPH dash hydrogen, okay? So that if I allow this electron pair to flow, it will attack and pick up the proton, and that would be an equivalent reaction. And so just not fully articulated because we now understand where that hydride is actually coming from.